If I've got a block, and I want to, it doesn't matter what it's made of, and I want to change the temperature of my block, then there's certain things that are going to affect that. To start with, I'm going to be writing some stuff down here. I'm just going to start off with some notation. This is the physics symbol for changing. It's a Greek delta, and it comes up in other equations as well, but it comes up in this one. And this is a Greek theta, so just a letter in the Greek alphabet. And this is a symbol that we use in physics for temperature. It's the one that AQA use anyway. Sometimes you see a capital T, but you never see a lowercase t because that's the symbol for time. So this means changing, that's what the triangle means, and then temperature, which is what this Greek theta means. Right, so if I want to change the temperature of this block, there's certain things I could do. And I'm going to start by trying to write out a little formula. I'm going to try and make up a formula, okay? So if I increase the energy that I put in, so I put in some energy, that's going to change the temperature of the block. The more energy I put in, the higher that temperature increase will be, or change in temperature will be. So I'm going to put an energy, right? E is the symbol I'm using for energy here. If I increase the energy, I increase the temperature afterwards. There's some other things involved as well. The mass of the block, how much kind of stuff is in it, which is what we call mass in physics. If the mass of the block is larger, then the temperature change is going to be lower. So I can't just put an M here for mass, because that would mean, if I did that, that would mean if the mass of the block was higher, the temperature change would be higher. And we want to say the opposite. So what I do is I put mass down here in a fraction. So now, if I increase the mass, look, that's going to reduce this number. There's another quantity as well in this equation that we need to consider. It depends what the block is made of. If it's made of metal, then actually not very much energy, and we're going to get quite a large temperature change. But if it's made of wood or something like that, then a lot of energy will be needed to change the temperature by the same amount. So that quantity is called specific heat capacity, and just the way that we define it, we put it here in our kind of fraction. What I've got then, if you rearrange this, and you can rearrange this using algebra or using a formula triangle to get energy on its own, but I'm left with a formula that's on the formula sheet. So I'm just going to times both sides by MC. I believe this is how you're taught to do it in maths. And so I end up with delta theta MC equals E. If I just rearrange this and just put it in a different order, energy equals mass times specific heat capacity times by temperature change. This formula is written on the formula sheet in your exam. You don't need to remember it. Also, you don't need to actually remember what the symbols represent, because the symbols and what they mean are also written on the formula sheet. So it's not the memory kind of game of formulas. It's taken out from this one. We don't have to worry about the kind of remembering stuff. Is that a good thing or not? I don't know. You might think, oh, it's a good thing, it's less I have to remember. But if you're better at remembering stuff than the average student in your year group in the whole country, then actually it's a disadvantage, because statistically we're just trying to beat everybody else in our exams. But you don't have to remember this one, it's on the formula sheet. So we might want to, this quantity C, this specific heat capacity, this is a symbol for specific heat capacity, we might want to measure it. And if we want to measure it, then actually we'll need to rearrange the equation in a different way. I'll just use the word rearrange. Change the subject of the equation is proper speak for it, isn't it? I should have said that. Okay, so if we want to find the specific heat capacity, we're going to need to make C the subject of this equation. C is the symbol for specific heat capacity. I should say, whilst we're here, lots of students often like to write, instead of C, they like to write specific heat capacity, SHC. Don't do that, because it looks like S times H times C, and it doesn't mean anything. There's a reason why we use standard symbols. It's so that everybody in the world actually knows what we're talking about when we do our maths and our calculations. So we use the C as a standard symbol, please, for specific heat capacity. So rearranging it, specific heat capacity, we want to get it on its own. So what I'm going to do is I'm going to divide both sides by mass times temperature change. And I end up with this. Now, normally we write the thing that we're interested in on the left, so I'll just do that. That's the same thing as above it. So I've got this formula. So if I want to measure the specific heat capacity of an object, which is a practical that you might be asked about, so required practical, then you need to be able to measure the energy that you're putting into it. You need to be able to measure its mass, and you need to be able to measure the change in temperature. So I'm just going to do that, show you the kind of setup that you might use. Okay, so I've got this block of metal. This is aluminium, and it's what we're going to be measuring the specific heat capacity of. And when we've measured it, we can, the specific heat capacity is a property of a material, so I can just look it up online and see if I'm right. So that's what we're going to do. First off, we need to find out the mass of this aluminium block, and the mass is 1.0019 kilograms. Now, that's so close to 1 kilogram. I'm just going to call it 1 kilogram. The other things that we're measuring, we can't measure them anywhere near that precisely. So we're just going to say that's 1 kilogram. And I've got this heater. This is how I'm going to put the energy into the block. So heater goes in there, and I should be able, if I can measure how much energy goes into this heater, I'm going to assume that all of the energy that I put into the heater makes it into the block. Now that's a bit of an assumption, because the heater, when I touch it up here, it will be hot up here. And so clearly some energy is coming from the heater to the air. So this is one of my assumptions in this, that all of the energy from the heater is going into the block, and it's quite a big assumption. I'm going to measure that energy with, this is plugged into a joule meter. So this is a joule meter over here. Now, if we do this experiment in school, when you come back, you won't be using a joule meter because we only have 2 of them. But we're going to use this to measure the energy that we're putting into our block at the moment. And that the heater is powered by this power pack, but it's just set on 12 volts. It's a 12-volt heater. Okay, so that's how I'm going to measure my energy. I've already measured the mass. I've got one thing left. If you think about your formula, specific heat capacity is energy divided by mass times temperature change. So I need to measure the temperature change. At the moment, well, so I'm going to put this thermometer in here. And at the moment, the temperature of the block is 19 degrees. Okay, so I'm just going to note that down. So I've called it temperature 1, and then I can call the final temperature, temperature 2. Now this is something that I'm going to do to make the experiment slightly more accurate, but it's not something that you necessarily have to write about in a method if you're asked to do that. This heater, when I turn it on, some of the energy that I'm putting into this circuit is just going to go into heating up the heater itself, because the heater's quite cold at the moment. So before I put the heater in there, I'm actually going to turn it on for 30 seconds before I do that. And you can see the value on the joule meter going up, but I'm just going to reset it once the heater's up to temperature. Okay, so heater's in, I've reset it. Here we go. Okay, so I don't think any more digits will fit on this screen, so I'm going to stop. Let me get up to here. There we go. Right. Okay, so I've turned it off. We put in 9,999 joules. So I'm going to write my energy here is 9,999. Oh dear, 99 joules. Capital J for joules, of course. Now, the temperature, you might think, oh, why didn't look at the temperature straight away? That's because the thermometer is going to take a bit of time to equilibrate. The energy needs to from the block needs to heat up the thermometer, and the thermometer will still continue to rise for a little bit. At the moment we're on 27. Okay, so we've made it to 28. Whilst I'm here though, actually, I'll just do a little bit about errors, because I did have the camera up here and it looks like 29 from up here. That's called parallax errors. If you're not in line with the thing that you're looking at, you're going to get an error when you take a reading. But if we take the reading properly, then we end up with 28. So final temperature is 28. So we've got these things. The mass, of course, was 1 kilogram that we measured earlier. Let's put units on this. So my formula that I derived earlier is specific heat capacity is energy divided by mass times change in temperature. So the energy that I had here was 9,999. The mass was 1, and the change in temperature is 28 to take away 19, which I guess put it up here. My change in temperature, which is 9 degrees C. So times 9, I can work out the specific heat capacity of aluminium, which actually gives me 1,111. And the units are the units are joules per kilogram degrees C. I get those units from the formula, if you just saw me with the pens there, joules per kilogram degrees C. There we go. You could put, you're actually allowed to put a slash in here as well because you don't have bid mass in units, and that's something that we'll address when we do A-level physics. But for this, a bit ambiguous, but we can just write this. Okay, when I look it up online though, the accepted value is 900 joules per kilogram degrees C. Why is there this difference? Well, we've overestimated energy. The energy that we put into the heater, some of it went into the air. So not all of this 9,999 went into the block. And that means that this value should be lower, but this is just what we've measured. It should be lower though. So if this value was lower, then actually the specific heat capacity would be lower, and then we'd be more like approaching 900. So there's quite a lot of uncertainty in this experiment. Some of the ways to minimize that are to heat up the heater before we start. I've also put in some glycerol in here as a thermal contact, but you can see there's still a bit of air in there. I should perhaps put more glycerol in, or oil I could put in there as well, to mean that actually we're not heating up the air in between the heater and the block, or actually in between the block and the thermometer, because the thermometer needs to also get up to the same temperature as the block for the experiment to work. But I've ended up with something close to 900, so I'm fairly happy with that.